In this video, I'm going to walk you through a few measurements to demonstrate the performance of the wideband IF digitizer of the PXA N9030A. We are going to make measurements to assess the signal to noise specifications as well as the spurious-free dynamic range specifications of the digitizer, which are probably two of the most important specifications of an IF digitizer. So let's get started. First, I'm going to put the analyzer into the IQ analyzer mode, where we can assess the full information bandwidth of the digitizer. I'm going to set the span to 160 MHz from the default value of 8 MHz so as to be able to assess the full information bandwidth of the digitizer. When making signal to noise measurements, here's one rule of thumb. We need to have the input signal close to the full scale of the ADC. Nominally speaking, that is minus 10 dBm at the input of the analyzer with 0 dB attenuation. So the signal is already coming in at minus 10 dBm, so I'm going to adjust the input attenuation to 0 dB. Next, let's set the analyzer for the best displayed average noise level, and we can accomplish that by setting the resolution bandwidth that is as narrow as possible. So for this span, 5 kHz would be an appropriate resolution bandwidth setting. Now I'm going to adjust the reference level and the scale such that we can see both the input signal and the noise floor. So I'm going to set the reference level appropriately, and then I'm going to adjust the scale so as to be able to look at the noise floor. Now we are able to see the noise floor and the input signal. Now let's place some markers to see what the noise floor looks like. So I'm going to set a marker that is 20 MHz offset from the main signal, and I'm going to place that marker on the spectrum average trace so that we can get a more stable reading. Now I'm going to turn the marker noise function, and we can see that the noise floor reading is coming out to be about minus 153 dBm in a 1 Hz bandwidth, which is a pretty impressive number. Now let's explore the signal to noise ratio, which is essentially this noise level relative to the full scale signal level. So let's use the delta marker to measure that. So we are seeing a signal to noise ratio measurement reading of about minus 143 dB in a 1 Hz bandwidth, which is a pretty good number. Now we can do even better by adjusting the input level such that it is as close to the clipping level of the ADC. So one way to do that is to increase the signal level at the input until we see an overload of the ADC, and then we can back off 1 dB. So I'm going to increase the amplitude of the signal in 1 dB increment, and notice this number here. It's at minus 143, and we'll see an improvement in that number as we increase the input level at the ADC close to the clipping level of the ADC. Now we see an input overload at the ADC, so we are going to back off a dB. So we have seen an improvement of about 2 dB by bringing the input signal close to the clipping level of the ADC. Now let's move on to looking at the spurious-free dynamic range of the Digitizer. Notice there doesn't appear to be any spurs showing up in the current spectrum trace. With the present settings, it appears that we have an SFDR which is close to 90 dB, which is very hard to believe. It just so happens that when the input signal is tuned to the exact center of the screen, in this case 1 gigahertz, and we've set the center frequency to be 1 gigahertz, all the harmonics generated by the ADC also fall at the center of the screen. In order to assess the true SFDR performance of the Digitizer, we need to move the signal away from the center of the screen. We provide SFDR specifications for a maximum of 12 MHz offset. So let's move the input signal that is 12 MHz offset from the center of the screen. So let me change the source frequency to 988 megahertz, which is 12 megahertz offset from 1 gigahertz. Now we notice some spurs. The highest spur we notice is the third harmonic. How do we know it's the third harmonic? When the signal frequency is shifted down by a certain number, the third harmonic moves up in frequency by a factor of 3 times that offset. So for the 12 megahertz shift down that we did on our input signal, the third harmonic should have moved up by 3 times 12, that is 36 megahertz, to make it a delta of 48 megahertz between the input signal and the third harmonic. So let's make that delta measurement between the two, the input signal and the third harmonic. So I'm going to go to my marker 1, place it on the peak, and then go to marker 2, and I will place it on the second peak, and now we'll see that the delta between the two is about minus 72 dB. Now we can do even better by backing off the level of the input signal at the ADC by about 3 to 4 dB. So let's do that. So I'm going to go into the amplitude, and I'm going to reduce the amplitude level by about 3 dB, and you would notice that there has been an improvement in the dB value from before. So what we have learned in this video is that in general, when you're making SNR measurements, you want your signal as high and close to the full scale of the ADC as possible, and when making SFDR measurement, you want the level to be backed off by 3 to 4 dB from the full scale level of the ADC. Thank you.